A single point of light contains the entire cosmic blueprint. This is the starting point for mapping the structure of reality, a journey that connects the strange world of quantum particles to the immense cosmic web of galaxies. By the end of this exploration, you will see the universe as a single, interconnected whole, where the rules governing the smallest particles dictate the fate of the largest structures. How did microscopic quantum fluctuations create the vast emptiness between galaxies? What invisible force is now tearing the cosmos apart? This map reveals a reality far stranger and more beautiful than it appears. What does it mean to live in a universe where everything is linked? Reality's deepest foundation is not made of solid matter, but of shimmering possibility. At the quantum scale, particles like electrons do not have a single, definite location. Instead, they exist as a cloud of probabilities, a haze of potential locations where they might be found. This is the principle of superposition, a concept famously illustrated by Erwin Schrödinger's thought experiment with a cat. In that scenario, a cat in a box is simultaneously alive and dead until someone looks inside, forcing a single reality to emerge. This seems absurd because our everyday world does not work this way, yet at the quantum level, this is the fundamental rule. Particles exist in multiple states at once until an observation, an interaction, collapses those possibilities into one concrete fact. Even more baffling is quantum entanglement, a mysterious connection where two particles become linked, change the state of one, and its partner instantly responds, no matter if they are across a lab or across the galaxy. This connection happens faster than light, seemingly ignoring the space between them. This quantum weirdness is not just a laboratory curiosity, it is the bedrock of existence. Every atom in your body, every molecule in the air you breathe, is built upon this strange and wondrous foundation of probability and connection. To grasp the immense structure of the cosmos, we must first accept that its blueprint is written in this language of potential. This quantum haze of potential is not scattered randomly, but is structured by an unseen architecture. The universe at its most fundamental level is not a collection of distinct particles, but a vast, interwoven tapestry of invisible fields. Picture an endless, calm ocean. This ocean is not water, it is a field of energy, a fundamental entity that fills all of space. Now, imagine a ripple moving across its surface. That ripple is what we call a particle. An electron is simply a tiny, persistent vibration in the universal electron field. A photon is a shimmer in the light field. Every type of fundamental particle is just a localized excitation in its own corresponding field, a wave on its own unique sea. This is the revolutionary perspective of quantum field theory, a framework that successfully wove together the strange rules of the quantum with Einstein's theory of special relativity. It was a monumental achievement pioneered by minds like Paul Dirac and Richard Feynman. This theory does more than just rename particles, it explains their very nature. It tells us how particles like the Higgs boson interact with other fields, granting them the property we experience as mass, essentially weaving the substance of reality itself. This leads to a profound shift in how we view emptiness. What we call the vacuum of space is not truly empty. It is this same underlying field, but in its calmest, lowest energy state. Yet, even there, it is seething with potential. Temporary particles and antiparticles constantly flicker in and out of existence, borrowing energy from the fabric of spacetime in a restless quantum dance. This vibrant, dynamic medium, the quantum vacuum, is the true foundation, Understanding these fundamental fields gives us our first crucial coordinate on the map of reality, a starting point from which we can trace the emergence of everything we see. From this vibrant quantum foundation rises a powerful yet incomplete cosmic rulebook. We call it the Standard Model of Particle Physics. Think of it not as a static chart, but as a dynamic set of instructions that governs how every fundamental piece of matter interacts. It is the universe's own constitution for the tiny world. The model organizes the known building blocks into a kind of ultimate periodic table. On one side, you have the quarks, which combine to form protons and neutrons. On the other, the leptons, a family that includes the familiar electron. Then there are the force carriers, the messengers that make interactions happen. The photon carries the electromagnetic force, the gluon binds quarks together with the strong force, and the W and Z bosons mediate the weak nuclear force responsible for radioactive decay. This model is a monumental achievement, the result of decades of work by thousands of scientists and massive machines like the Large Hadron Collider at CERN. It successfully describes 3 of the 4 fundamental forces that shape our reality. Yet for all its power, the Standard Model is famously unfinished. It cannot account for the force we feel every single day, gravity. It offers no explanation for the dark matter whose gravitational pull holds galaxies together. As the physicist Leon Lederman beautifully described it, the universe is a symphony of subatomic particles. We have learned to recognize many of the instruments, but the deepest notes of the composition, the bass line of gravity and the hidden rhythm of dark matter, remain silent to our current theories. This powerful rulebook is therefore a partial map, one that points directly toward the vast, unknown territories we are compelled to explore. Our incomplete cosmic rulebook leaves us standing at a precipice, staring into a deep conceptual chasm. On one side lies the universe of the very small, a realm of probability and discrete packets of energy governed by quantum mechanics. On the other side stretches the cosmos of the very large, where Einstein's general relativity describes gravity as the elegant warping of a smooth, continuous spacetime. These 2 pillars of modern physics are both spectacularly successful in their own domains, yet they are fundamentally, stubbornly incompatible. When their mathematical languages are forced to speak about the same event, such as the center of a black hole or the very first moment of the Big Bang, the result is nonsense, a storm of infinite values where physics breaks down completely. This is not a minor oversight, it is the central crisis of theoretical physics. The quest to resolve it, to find a single theory that weaves these 2 descriptions into one seamless whole, is the search for quantum gravity. It is the struggle to draw a single map that can guide you from the chaotic heart of an atom to the serene orbit of a planet. 2 fascinating paths have emerged from this struggle. The first, string theory, makes a breathtaking proposition. It suggests that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy, smaller than a proton by a factor of trillions. In this view, the universe is akin to a cosmic symphony. Just as different vibration patterns on a violin string produce distinct musical notes, the different resonant frequencies of these fundamental strings produce what we observe as electrons, quarks, photons, and every other particle. A single string vibrating one way is an electron, vibrating another way is a photon. Even the force of gravity carried by the hypothetical graviton would be just another note in this vibrational harmony. String theory ambitiously seeks to be a theory of everything, unifying all particles and all forces under one elegant vibrational principle. The other major contender, loop quantum gravity, takes a different, more geometric approach. It asks what spacetime itself is made of at the smallest possible scale. Instead of a smooth, continuous fabric, it proposes that space is woven from a network of finite, quantized loops, a spin network. Picture the fabric of reality not as a seamless silk sheet, but as a chainmail tunic with each interlinked ring representing a tiny, discrete parcel of space. There is a smallest possible unit of volume, a quantum of space, just as light comes in discrete packets called photons. Time, too, may advance in these tiny, fundamental steps. This theory directly quantizes the geometry of spacetime itself, offering a way to describe the universe without the infinities that plague other models, especially at the moment of the Big Bang. Which of these maps, the vibrational or the geometric, will ultimately guide us? The answer is locked within the birth of the universe, a realm where both theories must prove their worth. To find the domain where gravity and the quantum world finally meet, we must shrink our perspective to an almost inconceivable degree. This is the Planck scale, the universe's ultimate lower limit. Named for the physicist Max Planck, this is not merely another small measurement. It is the final frontier of smallness, a size below which the very ideas of distance and duration lose all meaning. At 10 to the negative 35 meters, a Planck length is so minuscule that if you enlarged a single atom to the size of the observable universe, a Planck length would be roughly the height of an average tree. At this incomprehensible scale, the smooth geometry of spacetime predicted by Einstein shatters. It is theorized to dissolve into a seething, turbulent froth, often called quantum foam. Here, tiny wormholes might blink in and out of existence, and the fabric of reality itself becomes a chaotic foam of possibilities. This is the resolution limit of the cosmos, the pixel size of existence. It is here, in this frenzied domain, that gravity finally sheds its cosmic cloak and reveals its quantum strength. At the Planck scale, the force of gravity becomes as potent as the electromagnetic and nuclear forces, a necessary condition for the theories of quantum gravity to take hold. This is the only arena where a graviton, the hypothetical particle of gravity, could truly be observed. Yet this realm is forever beyond the reach of any conceivable microscope. The energy required to probe such tiny distances is so immense that it would collapse into a black hole, instantly swallowing the experiment. So we are left with mathematics and the sheer power of human reason to guide us. To draw our map of reality, we must trust the equations that point to this chaotic, fundamental ground state of the universe. It is a place where our conventional understanding of existence is not just challenged, but completely rewritten. But this chaotic quantum foam held the seed of everything to come. In the very first fraction of a second, our universe underwent a transformation so violent and profound it defies all intuition. This was the era of cosmic inflation, a period of exponential expansion where spacetime itself stretched faster than the speed of light. The entire observable universe ballooned from a subatomic speck to something perhaps the size of a grapefruit in a span of time so short it makes a blink seem eternal. This idea, championed by physicist Alan Guth, was a revelation. It solved long-standing puzzles in one elegant sweep. Why is the universe so remarkably uniform in all directions, a concept known as the horizon problem? Because it all originated from a tiny, homogeneous patch that was inflated to a cosmic scale. Why is the geometry of space so flat? Because inflation stretched the fabric of spacetime so thin that any initial curvature was smoothed away, just as blowing up a balloon makes its surface appear flatter and flatter. But the most stunning connection lies in the origin of all structure. During this hyper-expansion, the universe was not perfectly calm. It was still a quantum realm, seething with tiny, random fluctuations in energy. These were microscopic ripples in the fabric of space-time itself. As inflation roared on, it stretched these quantum ripples to astronomical sizes. They became frozen into the cosmos as faint imprints, subtle variations in density that acted as gravitational seeds. The denser spots began to pull in more and more matter through gravity over billions of years. Those microscopic quantum jitters, magnified by inflation, became the blueprints for galaxy clusters, for individual galaxies, and for the vast, empty voids between them. The grand cosmic web, a tapestry of light and darkness on a scale of billions of light years, was directly sown by the random tremors of the quantum world. This explosive birth did not just create space, it gave it a structure, a destiny written in the first fleeting moments of existence. The violent expansion of inflation gave way to a universe flooded with a searing, primordial fire. For several 100,000 years, the cosmos remained an opaque, blistering plasma, a thick soup of fundamental particles where light could not travel freely. But in the very first minutes, a crucial, brief window opened for creation. As the universe expanded and cooled from its unimaginable birth heat, it reached a temperature where atomic nuclei could finally begin to form without being instantly torn apart. This was the era of Big Bang Nucleosynthesis, a fleeting period where the entire universe acted as a single, colossal nuclear fusion reactor. Governed by the precise strengths of the nuclear forces detailed in the Standard Model, protons and neutrons began to collide and stick. They first formed deuterium, a heavy form of hydrogen, and then rapidly fused into helium. In just a few minutes, the basic chemical identity of the cosmos was set. The calculations pioneered by physicists like George Gamow and his colleagues are breathtakingly precise. They predict that roughly 75% of the ordinary matter in the universe by mass should be hydrogen and about 25% helium, with only the tiniest trace of lithium. When astronomers look out at the oldest, most pristine clouds of gas in the universe, this is exactly what they find. The observed ratios match the theoretical predictions with stunning accuracy. This is not a coincidence. It is a direct confirmation that we understand the physics of the universe back to its earliest moments. This primordial soup of hydrogen and helium, the cooled ashes of the Big Bang, became the universal raw material. It was from this simple, elemental broth that gravity would later sculpt the first stars, the first galaxies, and ultimately, the planets and life that would one day arise to read this cosmic recipe. The fundamental particles had been organized into the first stable structures, and the map of reality now showed its most basic chemical landmarks. That primordial broth of hydrogen and helium filled a darkening cosmos, but for nearly 400,000 years, it remained a universe without a view. Then a pivotal transformation occurred. The expanding universe finally cooled enough for a fundamental shift, a moment of cosmic transparency. Electrons, which had been bouncing freely through the searing plasma, were now captured by atomic nuclei, forming the first stable atoms. In that instant, the fog lifted. The light that had been trapped, endlessly scattering off particles, was suddenly set free. This first flash of liberated light still fills the entire universe today, stretched and cooled by billions of years of expansion into a faint microwave glow. We call it the cosmic microwave background, and it is the oldest photograph ever taken. This is the universe's baby picture, a snapshot from its infancy. Its discovery in the 1960s was a stroke of serendipity. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in their antenna at Bell Labs. They pointed it in every direction, they even cleaned out pigeon droppings, but the faint, uniform static remained. They had accidentally stumbled upon the echo of creation itself, the cooled remnant of the universe's fiery birth. At first glance, this background glow appears incredibly smooth, a testament to the homogenizing effect of inflation. But when we look with exquisitely sensitive instruments, like the European Space Agency's Planck satellite, we see something breathtaking. Superimposed on that uniform canvas are tiny, mottled variations in temperature, tiny patches that are ever so slightly warmer or colder than the average. These anisotropies are not random noise. They are the fossilized imprints of those initial quantum fluctuations, the microscopic ripples in space-time that were magnified to cosmic proportions during inflation. This map of hot and cold spots is a Rosetta Stone for cosmology. It translates the quantum jitters of the newborn universe into a detailed blueprint for its future. Each slightly denser, warmer spot is a gravitational seed, a region where matter began to pool more densely under the pull of its own gravity. Over the next billions of years, these tiny seeds would be the nucleation points, the places where gravity would patiently gather the primordial gas, building the first stars, the first galaxies, and weaving the immense cosmic web. The faint pattern you see in a map of the cosmic microwave background is not just a relic. It is the direct link, the causal chain that connects the probabilistic haze of the quantum world to the majestic, structured cosmos we inhabit today. That faint pattern in the cosmic microwave background, the blueprint for all structure, contains a profound secret. The gravitational seeds we see etched into that ancient light were not strong enough on their own to build the galaxies we observe today. The blueprint required an unseen architect, a mysterious substance whose gravitational grip is the true sculptor of our cosmos. We call this invisible component dark matter. This is not merely an empty name for something we do not understand. We know it exists because we can watch its powerful hand at work. Look at a spiral galaxy like our own Milky Way, with its stars orbiting a central core. According to the laws of gravity, stars on the outer edges, far from the visible mass in the center, should move much more slowly than those near the middle. Think of the planets in our solar system, with distant Pluto crawling along its orbit while Mercury zips around the Sun. Yet when astronomers measured the orbital speeds of stars in distant galaxies, they found something astonishing. Stars on the outskirts were moving just as fast as those near the center. The entire galaxy was rotating as a single, rigid plate. The only plausible explanation is that each galaxy is embedded within a vast, massive sphere of something invisible, a dark matter halo whose gravity grips the outer stars, whipping them around at unexpectedly high speeds. We see this same invisible influence when we observe giant clusters of galaxies. Their immense gravity acts as a lens, warping the fabric of space-time so severely that light from more distant galaxies is bent and distorted as it passes through, a phenomenon known as gravitational lensing. When scientists map this distorted light, they find that the visible galaxies in the cluster account for only a tiny fraction of the total mass causing the warping. The rest, the overwhelming majority of the gravitational glue holding the entire cluster together, is dark matter. So what is this elusive substance? It cannot be made of the ordinary atoms we know, the protons, neutrons, and electrons of the Standard Model. It does not interact with light at all. It neither emits, absorbs, nor reflects it, which is why it is perfectly transparent and dark. The leading candidates are exotic particles that are relics from the universe's fiery beginning. One possibility is WIMP, or weakly interacting massive particles. As the name suggests, these would be heavy particles that feel gravity and the weak nuclear force, but not the electromagnetic force, allowing them to pass right through normal matter like a ghost. Another candidate is the action, an incredibly lightweight particle originally proposed to solve a different puzzle in particle physics. Whatever its identity, dark matter's role is absolutely fundamental. It formed first, collapsing under its own gravity into a vast, invisible web of filaments and halos. This web became the cosmic scaffolding, the underlying skeleton of the universe. The ordinary matter, the atoms that make up stars, planets, and us, was simply too energetic and diffuse to collapse on its own. It needed the deep gravitational wells carved out by dark matter to pool and condense. Without this invisible framework, the primordial gas would have remained a diffuse, formless haze. There would be no galaxies, no stars, no planets. Dark matter is the silent, unseen director of the cosmic drama, the hidden layer on our map that gives the visible universe its shape and form. That invisible dark matter scaffold provided the essential anchor, but the universe remained a silent, lightless expanse. Then, in the deep darkness, the first stars ignited. This was the cosmic dawn, a revolutionary period when the cosmos woke from its dark age and filled with the first brilliant points of light. These first-generation stars, known as population 3 stars, were nothing like our Sun. They were colossal behemoths, hundreds of times more massive, and they were pure, composed only of the primordial hydrogen and helium forged in the Big Bang's first minutes. Their nuclear furnaces burned with a ferocious intensity. Deep within their cores, they accomplished what the universe had never done before. They fused that simple hydrogen and helium into heavier elements. For the first time, carbon and oxygen were forged in stellar fire, the very building blocks of future planets and life itself. But these stars were doomed by their own brilliance. They lived fast and died young in cataclysmic supernova explosions, seeding the surrounding gas clouds with these newly minted heavy elements, enriching the cosmos for all the stars that would follow. Their light did more than just illuminate the void. It fundamentally changed the nature of the universe itself. Their intense ultraviolet radiation began to blast apart the neutral hydrogen atoms that filled space, stripping away their electrons in a process called reionization. This pivotal epoch transformed the universe from a neutral fog back into the transparent, ionized plasma that fills intergalactic space today. We are now witnessing this dramatic transition with powerful new eyes. The James Webb Space Telescope peers back in time, capturing the faint glow of these first galaxies as they flicker to life. Their formation was not a simple process. It was a complex, dynamic dance. Gravity pulled gas into the dark matter halos, the gas cooled and condensed to form stars, and then those stars fought back. Their intense radiation and eventual supernova explosions blew vast bubbles in the gas, heating it and pushing it away, regulating the formation of the next generation of stars. This delicate feedback loop, a battle between collapse and explosion, determined the size and shape of the first galaxies. This was the moment the cosmic blueprint, written in quantum ripples and sculpted by dark matter, finally became visible. The smooth, dark universe began to sparkle, tracing the first luminous outlines of the immense cosmic web we now call home. Gravity's patient work began with those first brilliant stars. But how does this force, so feeble between individual particles that it is utterly trumped by other interactions, become the master architect of the cosmos? The answer lies in a radical rethinking of gravity itself. It is not a pull in the traditional sense. Einstein's theory of general relativity revealed that gravity is the shape of reality. Mass and energy do not simply sit within space and time. They mold the very fabric of spacetime around them. Think of a stretched trampoline. Place a heavy bowling ball in its center, and it creates a deep, smooth depression. Now roll a marble across the fabric. It will not travel in a straight line. It will curve inward, orbiting the central weight. The marble is not being pulled by a mysterious force. It is simply following the shortest path through the curved geometry the bowling ball has created. This is the essence of gravity. The Sun creates a similar depression in the space-time of our solar system, and Earth, like the marble, follows that curved path in a stable orbit. This geometric nature of gravity has astonishing consequences. It means that even light, which has no mass, must follow these curves. When light from a distant galaxy travels past a massive cluster, its path is bent, warping and distorting the galaxy's image like a funhouse mirror. We call this gravitational lensing, and it is one of the most powerful pieces of evidence for Einstein's theory, allowing us to literally see the invisible contours of spacetime. This same curvature governs the grandest motion of all, the expansion of the universe itself. The collective mass and energy content of the cosmos determines whether this expansion continues forever, slows to a halt, or ultimately reverses. Yet for all its cosmic power, gravity works with infinite patience. It is a cumulative force. While electromagnetism can make two electrons fiercely repel, and the strong nuclear force can bind a nucleus with incredible strength, their influence is localized. Gravity, by contrast, is only attractive, and it never shuts off. Its influence adds up over immense distances and vast amounts of time. From the near-perfect smoothness of the early universe, gravity began its slow, relentless work. It amplified the tiny density variations imprinted from the quantum dawn, drawing dark matter and gas into the deepening wells of its own making. Over billions of years, this persistent, undramatic tug gathered diffused primordial hydrogen into stars, stars into galaxies, and galaxies into the vast, swirling clusters and the immense, empty voids we map today. Gravity is the primary pen, the one that never lifts from the page, tracing the intricate filigree of the cosmic web with painstaking, billion-year strokes. This cosmic web is the final, magnificent expression of gravity's patient work. If you could pull back far enough, viewing the universe not as a scattering of individual galaxies but as a single, colossal entity, you would see its true architecture. You would witness a vast, intricate network of galaxies, clusters, and superclusters, all strung along shimmering filaments that stretch for hundreds of millions of light years. Between these brilliant threads lie the cosmic voids, unimaginably vast deserts of near emptiness so large that a single one could contain thousands of galaxies with room to spare. This structure, a luminous sponge or a cosmic neural network, is the largest known pattern in existence. For a long time, this was just a theoretical prediction, the expected outcome of gravity acting on the seeds in the cosmic microwave background. Then, projects like the Sloan Digital Sky Survey began to turn the theory into a map. Using automated telescopes to meticulously catalog the positions of millions of galaxies, astronomers did not find a random scatter. They revealed a coherent, web-like pattern etched across the sky, a cosmic continent of clustered galaxies connected by great bridges of light and separated by abyssal dark voids. This is the final, majestic expression of the gravitational collapse that began with those quantum seeds. The same force that guides an apple's fall to the ground has, over billions of years, woven the largest structure we can possibly comprehend. This web is the ultimate testament, a living demonstration that the rules governing the spin of an electron are intimately connected to the fate of a supercluster. The universe is not a collection of separate things. It is a single, interconnected whole, from the quantum foam at its foundation to the brilliant, sprawling web of galaxies that traces its silhouette against the dark. Yet this magnificent cosmic web is not the final word. Just as we thought our map was nearing completion, a discovery in the late 20th century revealed a baffling new feature, a force that rewrites our understanding of cosmic destiny. Astronomers were observing distant supernovae, using them as cosmic mile markers to measure how the universe's expansion rate has changed over time. Everyone expected to find that the pull of gravity from all the matter in the cosmos was putting the brakes on this expansion, gradually slowing it down. Instead, they found the opposite. The expansion of the universe is not slowing at all. It is accelerating. Galaxies are flying apart from each other at a faster and faster rate. This was a staggering revelation, like throwing a ball into the air and watching it not only fail to fall back down, but shoot away into the sky at ever-increasing speed. Something is actively working against gravity's relentless pull, a mysterious repulsive force we call dark energy. This invisible component is not just a minor player. It makes up about 68% of the total energy density of the entire universe, dwarfing both dark matter and all the ordinary matter we can see. So what could it be? The leading candidate is a concept Einstein himself once proposed and then discarded: the cosmological constant. This idea suggests that empty space is not nothing, but has an intrinsic energy, a constant pressure that causes space-time itself to expand. The more space there is, the more of this repulsive energy exists, leading to a runaway acceleration. Another possibility is a dynamic energy field that changes over time, known as quintessence. Whatever its true nature, dark energy is now the dominant force on our cosmic map, and it dictates the ultimate fate of everything. Its relentless push is already influencing the growth of the cosmic web, effectively putting a ceiling on how large structures can become. In one possible future, this acceleration continues unchecked, leading to a big freeze where galaxies are torn so far apart that the universe becomes an ever-cooling, lonely, and dark expanse. The map of reality, it seems, is still being drawn, and its most powerful feature remains its greatest mystery. This accelerating expansion, driven by dark energy, seemed to settle the cosmic story. But our most precise measurements have now revealed a troubling crack in this elegant model. Astronomers call it the Hubble Tension, and it is a stubborn disagreement over the universe's current expansion rate, the Hubble constant. Think of it like trying to determine the exact speed of a car. One method involves studying the engine's initial roar, and the tire marks it left at the very start of its journey. This is what we do by analyzing the cosmic microwave background, the pristine snapshot of the infant universe. That data gives us one very precise number for the expansion speed. Another method is to look at the car right now, using nearby mile markers like supernova and variable stars to measure its present velocity directly. This local measurement gives us a different, equally precise number. The problem is, these two numbers do not match. The universe today appears to be expanding significantly faster than the early universe's blueprint says it should be. This is not a small experimental error. It is a persistent and growing discrepancy that has survived a decade of increasingly sophisticated observations. As Nobel laureate Adam Rees, a key figure in the discovery of dark energy, has pointed out, this tension is a compelling clue. It suggests that our inventory of the cosmos, our standard model of cosmology, might be missing a crucial ingredient. Perhaps a new type of neutrino, often called a sterile neutrino, adds an unexpected twist to the early universe's physics. Or maybe dark energy itself is not a constant force but one that has evolved over time, changing strength in a way we have not yet accounted for. This Hubble tension is a powerful reminder that our map of reality is not a final, engraved tablet. It is a living document, a work in progress that is subject to revision with every new piece of data. The cosmos is presenting us with a puzzle, and the solution may require us to redraw the very foundations of our cosmic cartography. This stubborn tension in our measurements points toward an even more radical horizon. The very laws of physics we have so carefully mapped, the constants that seem so finely tuned for our existence, might not be universal truths at all. They could be local ordinances. This idea pushes us to the absolute frontier of cosmology, to the multiverse hypothesis. What if our entire observable universe, from the quantum foam to the cosmic web, is just a single bubble in an infinite, frothing meta-ocean of other universes? This is not mere science fiction. It emerges as a natural, albeit speculative, consequence of our most ambitious theories. The concept of eternal inflation suggests that the explosive period that created our cosmos never truly stopped. It may be a perpetual engine, continuously spawning new bubble universes in an ever-expanding sea of inflating space. Each of these bubbles could undergo its own version of the Big Bang, cooling into a cosmos with its own unique properties. String theory adds another layer to this staggering possibility. The way its extra dimensions of space are compactified or curled up determines the physical laws and constants we observe. With an astronomically large number of possible configurations, each bubble universe could represent a different solution, a different set of rules. In one bubble, the strength of gravity might be 1,000 times stronger, preventing stars from ever forming. In another, the nuclear forces might be too weak to bind protons and neutrons, leaving only a soup of fundamental particles. Our universe, with its specific constants that allow for galaxies, planets, and life, would then be just one fortunate roll of the cosmic dice in a vast lottery of possibilities. We cannot, with our current understanding, ever observe these other universes. The space between them is inflating so rapidly that no light, no signal can ever cross the gap. This makes the multiverse a profound philosophical challenge as much as a scientific one. It redefines reality itself, suggesting that our entire cosmic map, for all its grandeur, may only chart a single island in an infinite archipelago of existence. Are the fundamental rules we seek to uncover truly fundamental, or are they merely the parochial customs of our own tiny cosmic neighborhood? This radical rethinking of reality suggests the cosmos might be a grand illusion. One of the most mind-bending concepts on our map is the holographic principle, an idea that challenges our most basic assumptions about space and information. Proposed by physicists Gerard T. Hooft and Leonard Susskind, it makes a staggering claim. All the information needed to describe everything within a volume of space, every particle, every force, every event, can be perfectly encoded on its two-dimensional boundary. Think of the security hologram on your credit card. It appears to be a three-dimensional object, but all of its information is stored on a flat, two-dimensional surface. The holographic principle suggests our universe might work in a similar way. The three-dimensional reality we experience, from the quantum dance inside an atom to the vast sweep of a galactic supercluster, could be a magnificent projection from a simpler, lower-dimensional reality that exists on the farthest cosmic horizon. This incredible idea did not emerge from pure speculation. It was forced upon us by the strange physics of black holes. When matter falls into a black hole, it vanishes behind the event horizon, seemingly erasing all information about what fell in. This violates a fundamental tenet of quantum mechanics, which states that information can never be truly destroyed. The resolution to this black hole information paradox came from studying a black hole's entropy, which is a measure of its hidden information or disorder. The work of Jacob Bekenstein and Stephen Hawking revealed something profound. The entropy of a black hole is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is precisely proportional to the surface area of its event horizon. A black hole's maximum information storage capacity is defined by its two-dimensional surface, not its three-dimensional interior. This was the crucial clue. If the most information-dense objects in the universe store their data on a surface, then perhaps every region of space does the same. Our perceived three-dimensional world could be a holographic projection from the two-dimensional surface of the cosmic horizon. This principle offers a breathtakingly elegant potential route to unifying gravity and quantum mechanics. In this view, gravity is not a fundamental force but an emergent phenomenon, a consequence of the quantum information entangled on the lower dimensional boundary. The map of reality, it seems, might be far stranger and more economical than we ever conceived, a cosmic projection whose source code is written on the skin of the universe. This delicate balance of cosmic constants is not an accident. It appears the universe is finely tuned for life. Consider the strength of gravity. If it were even slightly stronger, stars would burn their nuclear fuel too quickly, collapsing before life could ever emerge on an orbiting planet. If it were slightly weaker, matter would never have clumped together to form stars in the first place. The mass of the electron, the charge of the proton, the precise energy levels within a carbon atom, each of these fundamental values seems set within an incredibly narrow window that makes complex chemistry, and therefore life, possible. This is the puzzle of fine-tuning, a mystery that places us at the center of a profound question. Why does our map of reality show a cosmos that seems so perfectly arranged for our presence? The Anthropic Principle is the formal response to this enigma. In its simplest, least controversial form, the weak Anthropic Principle, it is a statement of obvious selection bias. We can only find ourselves in a universe that has the right conditions to produce us. It is not that the universe was designed for observers, but that observers can only exist in a universe that allows them. Imagine a puddle waking up and marveling at how perfectly the hole it occupies fits its shape. The puddle thinks the hole was designed just for it, not realizing it simply conformed to the pre-existing cavity. Our universe might be that hole, and we are the water that fits it so well. This weak form is a logical necessity, a simple constraint on our observations. But then there is the strong Anthropic Principle. This version is far more speculative and contentious. It proposes that the universe must, in some fundamental way, be compelled to allow for the emergence of conscious life. This is not just a statement about our lucky location, but about the laws of physics themselves. It hints that the cosmos has a teleological or goal-oriented aspect, with life and consciousness as a necessary endpoint. This idea sits at a turbulent crossroads where hard physics meets philosophy and even theology. It forces us to ask what kind of map we are actually reading. Does it reveal a universe that is inherently bio-friendly, one whose laws are written with the potential for mind? Or does our existence point toward the multiverse, that infinite froth of bubble universes? In that vast cosmic lottery, trillions of universes may be stillborn, with laws too chaotic or too rigid to support complexity. We, of course, find ourselves in one of the rare, lucky winners. Our finely tuned constants are not a miracle, but a statistical inevitability given an infinite number of roles. The map does not show a designed world, but a survivable one. The Anthropic Principle, in all its forms, reframes our entire quest. We are not just mapping an objective reality out there. We are mapping the only kind of reality that could ever include us as its cartographers. This fundamental tension between our maps of reality reaches its breaking point at the edge of a black hole. Here, the smooth cosmic geometry of general relativity collides head-on with the unbreakable quantum rule that information can never be destroyed. On one side of this conflict stands the event horizon, the point of no return. According to Einstein's theory, if you were to cross this boundary, you would notice nothing special. You would simply be pulled inexorably toward the central singularity, a point of infinite density where all known physics ceases to exist. From the perspective of the outside universe, you and every bit of information you carry, from your atomic structure to your memories, would be lost forever, seemingly erased from existence. This is a direct violation of quantum mechanics, which treats information as sacred and permanent. It can be scrambled, but it must be, in principle, recoverable. The crisis deepened with Stephen Hawking's revolutionary discovery. He realized that black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly leak a faint glow of particles, now known as Hawking radiation. This process causes the black hole to gradually lose mass and over eons evaporate completely. This raises an unbearable question. If the black hole vanishes, what happens to all the information about everything that ever fell in? Is it truly gone, or is it somehow preserved in the radiation? This is the black hole information paradox, and it is not a minor technicality. It is a fundamental clash between our two most powerful descriptions of nature, a glaring sign that our map of reality is missing a vital legend. To resolve this, physicists have been forced to propose radical solutions. One compelling idea is the Holographic Principle, which suggests that all the information about what falls into the black hole is not lost inside. Instead, it is perfectly encoded like a cosmic pixel on the two-dimensional surface of the event horizon. The three-dimensional interior, with its crushing singularity, is then a kind of projection from this shimmering, information-rich surface. An even more violent proposal is the firewall hypothesis. It suggests that the event horizon is not a peaceful place at all, but a blazing wall of ultra-high energy particles that would instantly incinerate anything crossing it. This firewall would prevent information from ever being lost inside by destroying the infalling object at the boundary, preserving its information in the resulting energy outburst. Both of these ideas, as strange as they sound, are attempts to force the quantum and cosmic maps to agree. Black holes are not just cosmic vacuum cleaners. They are the ultimate proving grounds, the extreme environments where the fabric of space-time is stressed to its absolute limit. What happens here must obey both the rules of the very small and the very large. Unlocking the secret of the information paradox is not just about understanding black holes. It is the key to deciphering the universal language that connects the quantum to the cosmic, revealing a single, coherent reality from the event horizon to the edge of the observable universe. Time flows like a river through our reality, but its current runs deeper than any clock can measure. This mysterious dimension is a fundamental axis on our map, yet its true nature remains one of physics' greatest puzzles. At the quantum scale, time appears in the equations as a smooth, continuous parameter, an unwavering backdrop against which the dance of particles unfolds. The precise ticking of an atomic clock, governed by the quantum vibrations of cesium atoms, relies on this very assumption. But what if this smooth flow is an illusion? Some of our most promising theories, like loop quantum gravity, suggest that time itself may not be fundamental. It could be emergent, a collective property that arises from the relationships between countless quantum events, much like the temperature of a gas emerges from the frantic motion of its individual molecules. If this is true, then the steady passage of time is a cosmic mirage, a story told by the underlying quantum structure of spacetime. Yet on the human and cosmic scale, we experience time in a very specific way. We remember the past but not the future. We see eggs scramble, but they never spontaneously unscramble. This is the arrow of time, the irreversible direction from order to disorder, governed by a concept called entropy. The universe began in a state of incredibly low entropy, a highly ordered and smooth configuration originating from the Big Bang. Think of a new deck of cards perfectly sorted by suit and value. That was our cosmic starting point. As time progresses, the deck gets shuffled. The universe moves from that pristine order toward maximum disorder, a state of thermal equilibrium where energy is evenly distributed and nothing new can happen. Why did the universe start in such a special, ordered state? The answer is likely tied to the initial conditions of cosmic inflation. That explosive period of expansion effectively reset the cosmic clock, winding it up from an ultra-smooth, low-entropy beginning. From the quantum oscillations that define a second to the relentless expansion stretching the fabric of space, time is the invisible thread connecting all scales of reality. Determining whether it is a fundamental building block or a beautiful emergent property is the final key to completing our unified map, revealing a cosmos where even the flow of time is woven from its quantum foundations. This search for a final master map drives physicists toward a single, elegant framework, a so-called theory of everything. The dream is a set of equations so profound that they could describe a quantum fluctuation, a supernova, and the cosmic web with equal authority. One of the most ambitious paths toward this goal is string theory. It makes a breathtaking leap, proposing that the fundamental building blocks of nature are not zero-dimensional points, but unimaginably tiny, one-dimensional loops of pure energy. These strings are so small that if an atom were enlarged to the size of our solar system, a string would be no larger than a tree on Earth. The theory's profound elegance lies in its simplicity. The only difference between an electron and a quark, between a photon and the particle of gravity, is the resonant frequency at which a string vibrates. Think of a violin string. Pluck it one way and you get one note, pluck it another and you get a different note. In this cosmic symphony, each distinct vibration corresponds to a different particle and its properties. This elegant idea naturally incorporates gravity into the quantum world, predicting the graviton, the long-sought quantum carrier of the gravitational force. Yet this beauty comes with a strange cost. For the mathematics of string theory to work consistently, the universe must have more than the three spatial dimensions we experience. It requires extra dimensions, perhaps 6 or 7 of them, all curled up and compactified into a complex miniature shape at the Planck scale, far beyond our ability to perceive directly. Despite its compelling theoretical appeal, string theory faces a monumental challenge. It has yet to make a single testable prediction that can be verified in a laboratory. Instead of one unique solution, it presents a vast landscape of possible universes, each with different physical laws and constants. We may simply live in one bubble in this cosmic landscape where the numbers allow for our existence. Competing with this vibrational approach is another profound endeavor, loop quantum gravity. This framework asks a different question. Instead of focusing on particles, it asks what space-time itself is made of. It proposes that space is not smooth and continuous, but is woven from a network of finite, quantized loops. Picture reality not as a smooth sheet, but as a fabric of interconnected rings, a cosmic chainmail. There is a smallest possible unit of space, a quantum of volume, and time itself may advance in these tiny, discrete steps. This theory directly quantizes the geometry of the cosmos, offering a way to describe the universe without the crippling infinities that appear at the heart of a black hole or the start of the Big Bang. Whether the final answer lies in the vibrational notes of strings or the woven geometry of spacetime, the quest itself is what matters. It is the human drive to draw a complete map, to find the singular principle from which all of reality, in its infinite variety, gracefully unfolds. But these intricate maps of reality all share a silent assumption that a clear line separates the observer from the observed. At the quantum scale, this line dissolves. The very act of looking seems to change what is there. This is the measurement problem, the most profound puzzle in all of physics. Before a particle is measured, it exists in a haze of potential, a superposition of all possible states, like a spinning coin that is simultaneously heads and tails. The moment we check, the coin lands decisively on one side. The wave function, that mathematical description of possibility, collapses into a single, solid fact. The Copenhagen interpretation, one of the earliest and most famous explanations, boldly assigns a special role to this act of observation. It suggests that the transition from the blurry quantum world to our definite classical reality requires a conscious observer. Does this mean that our minds, our awareness, are the very instruments that solidify reality from a sea of probability? It is a staggering thought that the cosmos might remain in a state of ghostly potential until a conscious being looks upon it. Yet many physicists argue this gives far too much weight to consciousness. They point to a process called decoherence. Imagine that spinning quantum coin. The instant it interacts with its environment, bouncing off a single air molecule or emitting a stray photon, its fragile superposition is destroyed. It becomes entangled with the vast, complex world around it, effectively forcing it to choose a state. In this view, a conscious observer is not necessary. The constant, noisy bumping of the universe itself is enough to collapse the wave function. So where does this leave us, the conscious mappers? We are caught in a strange loop. Our most fundamental scientific tool is observation, yet the act of observing seems to be woven into the fabric of what we are trying to see. We are not just passive cartographers charting a pre-existing landscape. We may be active participants, our very presence influencing the territory we seek to map. This bridges the deepest of divides, the one between the objective world of science and the subjective world of experience. Is the mind a separate phenomenon reading the cosmic code, or is it an inseparable part of that code, writing itself into existence with every glance? Yet these profound questions are not answered by thought alone. They demand tools of immense power and precision, instruments that extend our senses into realms forever hidden from our eyes. To chart the quantum haze, we must build machines that can peer into the heart of matter itself. The Large Hadron Collider at CERN is a cathedral of such technology, a 27-kilometer ring buried deep beneath the French-Swiss border. Inside its circular tunnel, protons are accelerated to within a whisper of the speed of light, and then steered into a head-on collision. In the fleeting, fiery aftermath of these crashes, for a fraction of a second, energy condenses back into particles, recreating conditions that have not existed since the first moments of the Big Bang. It was here that the final piece of the Standard Model, the Higgs boson, was finally snared from the data, a monumental discovery that confirmed how particles acquire their mass. This machine and others like it are our quantum microscopes, allowing us to probe the fundamental fields and forces that weave the fabric of reality. But our map must also span the cosmic scale. For this, we have sent our eyes into the heavens. The Hubble Space Telescope, freed from the shimmering distortions of Earth's atmosphere, has delivered pristine images of the deep universe, revealing galaxies in their infancy. The Chandra X-ray Observatory sees the high-energy universe, the searing hot gas in galaxy clusters, and the violent neighborhoods of black holes. And now, the James Webb Space Telescope peers even further back in time. its infrared gaze piercing the cosmic dust to witness the very first stars and galaxies igniting in the darkness. Each telescope observes a different wavelength of light, painting a unique layer of the cosmic portrait. We are no longer passive observers of the sky. We have learned to listen to the universe as well. Facilities like LIGO and Virgo are not telescopes in any conventional sense. They are colossal, L-shaped instruments designed to detect the most subtle of tremors, ripples in space-time itself called gravitational waves. When two black holes or neutron stars spiral into each other in a final, violent dance, they send shudders through the fabric of reality that travel across billions of light years. By the time they reach us, these waves have stretched and squeezed space by a distance far smaller than a single proton. The ability to measure such an infinitesimal distortion is one of the most astonishing technological feats humanity has ever accomplished. It has opened an entirely new sense, allowing us to hear the cosmos and to read the universe's oldest fossil, the cosmic microwave background. We launched the Planck satellite. Its exquisitely sensitive instruments mapped the faint temperature variations in that primordial light with unparalleled precision, giving us the most detailed blueprint of the young cosmos ever created. Each of these technological marvels is a different kind of brush on our cosmic canvas. Particle accelerators probe the quantum underpainting. Space telescopes fill in the brilliant details of stars and galaxies. Gravitational wave detectors trace the invisible contours of warped space-time, and satellites like Planck record the faint outline of the original sketch. Together, they allow us to draw a map that connects the smallest vibration of a string to the largest filament of the cosmic web. The ongoing advancement of these tools promises not just to add finer detail to our existing chart, but to reveal entirely new continents of reality waiting to be explored. Our maps of reality are not the territory itself. They are brilliant, evolving creations of the human mind, forged in the fire of our curiosity. Every scientific theory, from Newton's clockwork universe to Einstein's curved spacetime, has been a powerful but provisional guide. Each one worked beautifully within its domain, making stunningly accurate predictions, yet each was eventually refined or replaced when we peered a little deeper into the cosmos or a little closer into the atom. This is not a failure of science, it is its very essence. Our understanding is a living process, a conversation with the universe where every answer uncovers a more profound question. So we must ask, are these maps true descriptions of an objective world, or are they simply incredibly useful tools for prediction and control? The history of physics suggests they are models, limited by the very nature of our perception and the tools we use to extend it. We are like sailors charting an unknown ocean from the deck of a ship, mapping the coastlines we can see but forever wondering what lies beyond the horizon. Some horizons may be permanent. The Planck length, that ultimate pixel of reality, might represent a fundamental resolution limit for the cosmos, the edge of the observable universe from which light has not had time to reach us, defines a permanent causal boundary to our knowledge. We are confined to our cosmic horizon, unable to ever see what lies beyond its veil. This realization is deeply humbling. It tells us that there may be fundamental truths about existence that are forever beyond our grasp. Yet this limitation does not diminish the grandeur of our quest, it elevates it. The drive to map, to understand, to find our place in the great scheme of things is a fundamental part of what it means to be human. We are the universe awakening to itself, piece by piece, map by map, gazing into the mysterious depths from which we came and finding, not final answers, but a never-ending story of wonder. From the quantum haze to the galactic supercluster, a single thread of causality connects them all. our journey reveals a cosmos built upon a foundation of chance, where random quantum jitters in the first fleeting moments were stretched into the cosmic blueprint by a violent inflationary surge. These microscopic ripples, frozen into the fabric of space-time, became the gravitational seeds for everything to come. Acting upon this primordial blueprint was the invisible hand of dark matter, a mysterious substance whose silent gravitational pull provided the essential scaffolding. It gathered the diffuse primordial gas into the deep wells of its influence, allowing the first stars to ignite and begin their alchemical work. Within those stellar furnaces, the simple hydrogen and helium from the Big Bang were forged into the heavier elements, the very stuff of planets and life, all governed by the precise rules of the Standard Model. Now, dark energy dictates the future, its mysterious repulsive force accelerating the expansion of the cosmic web it helped to create. This is not a story of separate domains. The same fundamental forces that bind a quark within a proton also guide the orbit of a moon. The same mathematics that describes the probabilistic dance of an electron also charts the majestic trajectory of a galaxy. The universe operates as a single, coherent system. The fuzzy uncertainty of the Planck scale and the grand architecture of superclusters are not opposites. They are the two ends of a single, magnificent spectrum of existence, a seamless tapestry woven from the same fundamental laws. We are not merely observers of this tapestry, we are a part of its intricate weave, our very existence a testament to its profound and beautiful unity. Our journey across the scales of existence reveals a universe of breathtaking unity. We have traveled from the ghostly haze of quantum potential to the grand, luminous architecture of the cosmic web, tracing the invisible threads that bind them into a single, coherent whole. The same fundamental rules that govern the spin of an electron dictate the majestic dance of galaxies. The random tremors of the quantum world, magnified by the violence of inflation, became the very blueprint for the voids and filaments we map today. Our exploration confirms a profound truth that the cosmos is not a collection of separate things, but an interconnected system where the smallest scales and the largest structures are in constant, silent conversation. Yet for all we have mapped, the deepest mysteries persist. The dark matter that sculpts the cosmos and the dark energy that drives its acceleration remain enigmatic, reminding us that our chart is a living document, forever open to revision and wonder. This is not a story of cold, impersonal forces, but one of elegant, underlying order and staggering beauty. As Carl Sagan so eloquently put it, we are a way for the cosmos to know itself. The atoms that forged the first stars now form the very eyes that gaze back at the night sky. So the next time you look up, see it not as a distant, foreign void, but as a familiar landscape. You are not just looking out into the universe, you are looking at a part of the same reality that constitutes you, a single note in its ongoing, magnificent symphony. We would love to hear what you find most awe-inspiring about this interconnected cosmos. Share your thoughts in the comments and subscribe for more voyages to the frontiers of